Hey everyone, my name is Emil Koman. I'm with the University of Connecticut Department of Public Health Sciences, and I'm here with a collaborator introducing a demonstration using Excel on basic statistical tests.
Yes. Hi, everyone. My name is Sachi, and I'm with the Statistics Department at the University of Connecticut. And as Emil said, today we'll be presenting an introduction to investigating the relationships between variables, both categorical and continuous on Excel. This video will take a conversational approach, so Emil will explain some key concepts, and both of us will go in and jump in with questions to represent what an audience member might be wondering. Next, we'll dive into the larger plan for the series.
So this is supposed to be the first session of several probably, but the data and the demonstration that we built into Excel are posted online. There is an OSF location here, and there is a tiny URL. We're going to post them in the comments so you can access them and you can follow along while we demonstrate it in here. But you can also borrow from our worksheet and use formulas and adapt it to your data.
Absolutely. So we're through this Excel document, we'll be looking at three different research questions and also three different types of analysis, chi-squared, t-tests, and f-tests. We'll be dividing our explanations into the three different research questions, and we'll be starting with research question one. This research question goes into the categorical relation with independent samples.
So we're going to look at some variables that have an actual meaning for many folks, and they come from some real data that is also included in the Excel file. It's raw DPP data in here. We will be using as an example weight in the form of body mass index, and down the road in another research question, A1C or hemoglobin A1C, and gender. But the logic of the file is following some color coding scheme that we came up with. So whenever you see an orange color, there's some instruction, there is something to do, or there is some kind of explanation. The yellow highlights are going to show sections where something is needed. So you need to write in something or enter some number, otherwise nothing comes out. In the blue ones, there are usually numbers that will be popping up, meaning there's some formula and we're deriving some numbers that way. At the end, the green will show the result or the conclusion. And there's also a purple highlight that we're using. Whenever we use a formula, we're just trying to show you what the formula is actually saying, so you don't have to click around and figure it out. So we're going to use, I'm going to introduce the variables quickly. The BMI, which is body mass index, has values around 20, 30, but in this real data, the two groups, females and males, have different average values of BMIs, and that's what we're trying to replicate in here. A group of 10 only cases that will mimic females, that we will have some values around a mean of 33.4. So we're actually generating data using this formula. That's why it's in the purple color, meaning we're generating normally distributed variables with a mean of 33.4 and a standard deviation of 6.6. And another one, which has a different mean, it's supposed to actually mimic a mean of about 28. It's an error here. But in the end, what we are ending up with are 10 values that range around this mean. If we compute the mean using the Excel average formula, which pretty much is asking for the average of the 10 values, you're going to see the average. And for the second group, which is supposed to mimic the males, the average is going to have a different value. If we rearrange this data, for the 10 males and 10 females in columns, which is how data usually comes in, or we usually look at the data in this way, meaning we have BMI in one column and then gender coded in another column, and we code gender as female 1 and male 0. This is the data we're going to look at for the first analysis to answer the first question, which is, are there more overweight males than females? To do that, we have to recode the overweight or the BMI using Excel formula, which pretty much splits the 10 males and the 10 females into normal weight and overweight. So if we do that, what we're seeing in this new column that we generated are two new values for each person possible, 0 or 1. 0 means normal weight, 1 is overweight. And as you can see, if we just walk through this new variable, we see there are more ones in the first section of the data, which is males, than in the second section. Just visually, there seems to be something going on. But the way to analyze this data using a formal statistical test is to reshape it, meaning to build a pivot table out of the two columns in which the data is shown as a cross tabulation, meaning we're looking at males and females in rows and then normal weight, overweight in columns. So within each cell, we see the combination of the two binary categories. How many males are normal weight, how many males are overweight. It's normal weight and overweight. The total sample is 20. The row totals and column totals are shown in here.
As many people may remember, chi-square tests are used in genetics to understand if expected outcomes match observed outcomes. So, Emil, how do we calculate the expected outcomes for this kind of data?
That's a good question, because most of the statistical tests, including the chi-square test, use this kind of logic, which is what's observed. And in our case, this is what's observed. That's why we posted this data in a table in this format, meaning we have now yellow values in here versus what's expected, and what's expected under certain assumptions or conditions. So in this logic, the chi-square test is comparing observed values against expected values that we're going to show how to compute under the assumption that the two variables are independent. So if there is an independence null hypothesis, so to say, then we would expect these values. The way we calculate them is somewhat simple, and you can click on the formula. Each cell value is the product of the column total, row total, column total divided by the overall total. But that applies if the two variables are independent. So we do see different values, 1973, than the expected values if there was no relationship between gender and being overweight. And the question is, to what extent our numbers differ too much from the independence or null hypothesis or no relationship numbers, so that we may conclude there is a relationship.
How can Excel do? Great. How can Excel do the chi-square test for us?
That's how this one is. This section is showing. It's actually very simple, and that's why we're showing the formula in two ways. We're showing it in the purple section as the formula itself, but also when you click on the calculation, which is giving us an actual value, if you click on this, section here, it's actually highlighting what numbers are compared. So the actual range, which is what Excel calls it, or the observed values are compared to the expected range or the expected values under the assumption of independence. And the result is an average kind of discrepancy between the four values and the four values. So the larger such value means the more discrepancy we see between the numbers. This number already looks small, but we formally compare it to a critical value. And for our setup, for just two categories, and two categories, the critical value is 3.841, and this one can be computed in Excel too, meaning we can ask for the actual critical value under certain assumptions. This is supposed to be probably 20 here because that's the sample size, but that's the formula we're running. And the only other step needed to decide whether this is formally a big difference or not, besides just comparing the two numbers, and 0.006 is much lower than 3.8, is, and that's a parallel kind of judgment, looking at the p-value or probability of observing something like we observe if the null hypothesis was true. So the p-value usually has to be very small to reject the null hypothesis, meaning we find something or we find a relationship if the p-value is very small. It's not. It's actually very large. It's near 1. So go ahead.
Okay, what does that give us an answer for our original research question? How can we interpret that?
So if we read either the chi-square value, the chi-square statistic value observed compared to the critical one or the p-value, the conclusion is that the two binary variables that we looked at, overweight and gender, biological gender, are not related. Or rephrased, the answer to our question is that males and females do not have different rates of being overweight, or they have similar overweight rates. Even though, again, we do see some differences. In other words, there does seem to be a few more of these folks being overweight in one group than the other one, compared to the expected values. The difference is not large enough. So we're not rejecting the null hypothesis, so to say. We don't see a relationship between these variables. There is another little section in here which you guys should play with, and the colors are switched. And that's why this section is called what if. What if is if we start with the same row totals and column totals, we can also explore to what extent changing the numbers inside this table will change the conclusion. And you can play with that. But pretty much you can modify this number and see what happens along the way. This is a different kind of experiment here. We also have this question answered in a second way, in a second manner, using another test, even though this moves us into a different logic. We can also answer the question if the males, these males and these females, are different in their body mass index by using the continuous variables, the two BMI columns, initial columns. The way to do that is to actually compare the two means in a formal test, and that's a t-test of independent samples. So that's why this one is called one categorical predictor, one continuous outcome, because the outcome is BMI and the predictor is gender. So the question here is, to what extent being male will make you more likely to have a higher BMI or a lower BMI? So the t-test here is pretty much run directly into Excel. There is a screenshot of how to do it. It's a very simple operation. You just go to data analysis, and you choose t-test. So you just follow the instructions. The result is shown in here. And we also replicate this by hand. Again, we're just going to jump to the conclusion, which is the p-value, which is one of the most important ingredients, final ingredients, or the t statistic value, which is similar to a chi-square statistic, meaning it's a test that shows us to what extent we have something unusual happening if the null hypothesis is true. And that's how we accept or reject the null hypothesis. In this instance, the null hypothesis is that the two means are equal, or that the mean difference is 0. And if we reject this hypothesis, then we conclude there is a difference between the two means, a statistically significant. In this case, the p-value, which is very small, says that it's unlikely, it's very unlikely, unlikely, 4%, 4 times in 100 such cases, to see such a large difference if the two values were the same in the two populations of males and females. So we're saying, in other words, that these two values, these two means, the original continuous BMI appear to be different. Again, using the t-test, we seem to be seeing a difference between males and females. Using a chi-square test of the categorical overweight versus normal weight, we concluded something else.
Absolutely. And if anyone has questions about this later on, please put them in the comments and we can address this method in more detail in a next video.
Thank you. So the next session, we will be coming back with another research question and more answers. Thank you.